So I was given this boat cup holder to remake it. It's made out of, looks like some kind of fiberglass kind of material. You can see that it's really, really cracked. The water has pooled through and broken these holes. They are not factory, it looks like. Cup holders here, and I noticed that the glue is broken on the cup holder, so let's knock that out. So what we need to do is remake this part. This part we can reuse, nothing's wrong with it. Let's somehow get some measurements off of this and go from there. So what I'm going to start with, so I'm going to take this and I'm going to line it right up to my rails right here. I'm going to line this tape measure roughly up to there. Sorry, I'm doing this one-handed. And we can see that this is pretty close to 15 inches. So let's call it 15 inches this way. And since it's a isosceles triangle where these two legs are the same length, it's also 15 inches that way. The reason why I had it lined up here is since we have this curve here, it's really hard to measure where the edges is the same distance from here to here as it is from this way to this way in this direction. Next, we need to know how much of a curve this is. Let's put that there at the 15. Let's count back. 1, 2, 3, 4. And about the curve ends at around 4.5 inches. So let's say from the outer edge to the center of that circle, which is the radius, that'd be 4.5 inches. So this would have a 9-inch diameter. So next we need to know how this attached. So it looked like at one point there was a metal rod that went all around here that was bent. You can actually see the discoloration of where it was compared to where it wasn't. And we can see that that was roughly 1.5 inches of room. The metal rod sat inside this channel, which means this kind of went around it. The new design is going to sit on top of it. That way, so it looks cleaner from the outside. You'll see later when we mount it. What next do we need? We need to know the size of the circle. And at first you may think, let's measure what the circle's diameter here. But that's already using information that, well, look how rough this edge is right here. It looks terrible. Let's actually measure what's going to go in it. And since today we're not working millimeters, I switched it to inches and fractions. Since we actually want our hole to be a little bit bigger, since we're going to be gluing it back anyway. And I've already measured this, so don't worry about the accuracy. I'm just showing you how I did it. And all I did was I tried to go all the way around, find the biggest spot. And you may think, oh, this is a circle. Well, you only need to measure it once. Well, it turns out this is not a perfect circle. By quite a bit, actually. You can see if I hold it tight here, when I spin it, it's actually getting tighter, so I have to open up the calipers a little bit, and it's starting getting smaller. So we know their biggest point is around about here-ish, and it gets pretty tight right around there. I'm going to read that, and that says, oh good, that's the measurement I got earlier. It says 3 inches and 83/128. Next piece of information we'll need is this little corner right here, and you can see that there's no material here because that's actually where the rod went through. That's a roughly 2-inch diameter, so 1-inch radius circle. Doesn't really matter. It's not critical to any of this. It's just purely aesthetic. And of course, we want to add this little channel in here, and I'll show you how we can do that really simply in a second. So it's now the time to get into the beginning part of what is the difference between CAD versus CAM. CAD, which stands for Computer Aided Design, is basically where we take this and we take those measurements that we just got off of it and we put it into the computer and we model it. Let's do that here. So this is the model that I came up with. It looks fairly complicated, but trust me, it's not. Down here is our timeline. These are all the features and things that we've added to this model. And you see there's actually not very many. Sometimes this gets so long that there's a scroll bar up here, but that's for much, much bigger models. There's only a handful here. 12 features that we had to use. And realistically, we could probably get that down a lot more. But I tried to make this parametric and a little bit easier for myself. Parametric means that you can change designs and it should auto-update the model, which I've had to do 3 times, as you can see. This is my 3rd revision of this, which means I designed it once, needed to do a change, and needed to do one more change after that. And that's just because of a few little things. So let's go over this. So this is the original sketch. It's 15 inches here, and since it's based off of an isosceles triangle, it's 15 inches here as well. You can see that our big circle here is 4.5 inches like we measured. This inner circle here says 3 and 21/32 inches, which is what we measured as the inner circle. Pretty basic. And so what I did from there After I sketched it, we did an extrusion, which is basically just making that 2D drawing into a 3D object, just adding a little bit of height to it. And I just did some rounding of the corners, and then I drew another sketch. This is where I wanted the dish. So what I did is I took the outside border, I did an offset by 1¼ inches, and then to make sure I had that same distance from the circle here, I took another offset from the circle. You can see that we have our 2 overlapping boundary areas. So from there, we just did a simple extrusion, which just cut that out. Did a little bit more rounding, did a fillet all the way around it, drew another sketch, and this was actually for a feature that I didn't actually end up using. At least part of it is. Now this looks a little bit more complicated, and truthfully it's not really. All I did is I just made a circle that was tangent, that was the center of this curve, both here and up here, and these other circles over here are mounting hole locations. That's where that I had planned to make mounts for, but I never ended up actually using them. Here with our extrusion, we cut out our drainage holes out of the center tangent area. You can see those little divots there are the markings I was talking about we didn't end up using. Even though they're on our model here, I'll show you why we didn't end up using them. This other little feature right here, it looks like nothing happened, is our hidden body for the stock. This is just for me figuring out what the actual material roughly looks like to the computer. And then here I rotated it that way so we can get it aligned with our piece of wood, and that'll come up later. So that's the design. It's pretty darn simple. It's basically a few sketches with some extrusions and some just nice little filleting, some rounding, and just little drainage holes. It's that basic. So now that it's modeled and we know the little things that we have to adjust for, we need to somehow make it from a piece of wood, which is the material of choice for this project, and turn it into something this shape like our model. So how do we get from that model to something like this? Well, we can't just take our 3D model and, grab it out of the computer. We have to somehow tell this machine right here what we actually need to do. So now that we've designed this part in the computer, we have to tell this machine how to make it. And since you might not know how to make something if I hand you a model, we have to tell you how to do it. So we have to tell this machine how to do it. And since I know this machine, we made design decisions on this to make sure that this machine is capable of actually making this. And since the design is mostly 2D, we have our outside outline, we have our line around where the circle should be, we have basically this line of where we have our little tray and everything in here, but it has some depth. So since this is mainly a 2D design with a little bit of depth, that is along the third axis, let's call this our X and call this our Y, like a coordinate plane. So let's call this our Z-axis facing the camera. All of our main features are along the X and Y, but we have some depth, but it's perfectly in the direction of the Z-axis. There's no changes along the Z-axis that make the X and Y change. AKA, as this depth of this tray goes down, we're not making any X and Y changes. It's staying within that Z-axis, no other changes. Traditionally call this 2.5D, which means we need a machine that's capable of 2.5D. Thankfully, this is a CNC machine, this is a CNC router, and specifically what makes that is this is a machine that's controlled numerically, so it's a computer numerical controller. What is it doing? What is the computer controlling? It's controlling a router, aka spindle. It's something that cuts with an end mill. Let me grab one. Like here's a super long end mill. This is a 4-inch end mill with a 1.5-inch cutting area, and that's 1/4 inch in diameter. This is not what I'll be using. I will be using one of these. Basically same thing, just a little bit shorter. The shorter the bit, the more rigidity you have. So while we can cut in 3 dimensions with this machine, we can only cut from top down. And that's important because whatever features we do on this, if I want to cut from the sides or from the back, we'd have to flip it. We have to put it in some kind of weird jig or something. But we know that whatever features we need to cut from this needs to be cut only from the top in this Z-axis. So if I lay this down right here like that, I know the machine is only going to cut up and down or sideways, which is perfect because we can cut all the way around, channel this all out, pull out. And the cool thing about this still being a 3D machine is see how there's like a little bit of a curvature here and everything. It's called a fillet or fillet. I don't care. I pronounce it as fillet. Anyway, but we can add in that curvature in software by telling the machine how to do it. And now that we know the kind of constraints that we have, let's tell the computer how to tell this machine how to cut this. And that is CAM. CAD is not telling the machine how to cut it. CAD is telling the computer what the model is. CAM is telling the machine how to cut something in the shape of that model. So after all that rambling, hopefully that made sense. Let's tell the computer how to do it now. This part is where most people have the most confusion with. Yes, we have this 3D model here, but we can't just tell the CNC machine to cut this. We have to tell it how should it cut it, like which areas, how deep, what general dimensions does it need to cut in, and all that information. So we go from our design tab, and we go to our manufacture tab. And you can see that this yellow area right here, that's our stock material. That's the last thing I showed you when I was modeling it. Because this is kind of the confusing part. It's realistically not, it looks like there's a lot of steps. Like here, we can see this is called a facing operation, where we just clean up the top of it. In my first attempt, I do this manually, and I show you what it's like when I have to physically do it. Otherwise, we can literally just click up here. Otherwise, we can just click up here and click face, and we just set some settings. Here, I'll show you. We just set like our spindle speed and some other like movement speed stuff, where we actually want to be surfaced, aka everything within this yellow region is going to be cut, how deep it's going to be cut, aka I have it set here to the highest part of the model, how many passes it's going to take. So I told it it can maximum step down, aka each layer is a maximum of 1 millimeter, basically how it should move. Basic things like that. It figures out all of this movement area. It figures out all of that. And then the next thing I told it to do is I want it to cut out this pocket in here. What it's simply doing, as I'll show you here in edit as well, is I'm telling it, again, the spindle speed and everything, how fast it should move. I'm telling it should cut in this inner area. I'm telling it how high it should cut, aka the lowest point of this that it should be cutting is this contour that we selected here with that blue. How many times it should cut, should maximum cut 2 millimeters per every single layer that it goes down, because it'll cut a layer, go down, cut a layer, and basically just other little bits of information, really simple like that. So essentially, when we hit OK here, what it does is it finds the outer area, does a bunch of offsets. It starts cutting from the inner offset, cuts that, goes to one outer, goes to one outer, goes to one outer, and it keeps doing that until it's cut that entire layer, and then it drops down, starts from the center again, and does that all over again. Then next, we have our drilling operation, which is literally just me selecting these two holes. I'm telling it, once again, how fast, how far it can drill, how often it should be pulling the tool out. Next, this is the fillet I was talking about. This is kind of where it transitions from 2.5D to 3D. But basically, it's just found this perimeter and it just keeps on making a curve all around. Then we cut out most of the circle here, and I say most because we have these little tabs in there. And those tabs are to make sure that this circle disc doesn't fling out anywhere. It doesn't jam the bit as it's cutting. Because you can see the bit, obviously it's cutting the same width as the hole it's making. So it's just making sure that if this shifts, it doesn't bind the bit or anything. Makes it easier for cleanup later too. And I do that for mostly on the outside too, but you can see here, I actually didn't cut through the whole thing on the outside. And that's because of where our clamps are located at. And additionally, it's because of this flow, which is again another fillet around the whole edge. I just want to make sure I had enough strength of the material that we're cutting, the wood. The area that's being clamped is still strong enough to the main wood. And then after that, we cut out the rest of the part, and we still remain some tabs in there every so often. And it looks like there's not any tabs on this side here. You can actually see in the toolpath that makes that little jump. So they are there. It's just the stock material that I showed it is not big enough to actually visualize it here. Yet it is still doing it, and the toolpath still shows it. You may have noticed that I did skip this one operation called drill. And the reason why that's not there anymore, and there's no visualization for any of this, is because that is a suppressed feature, which is when you want to remove a feature, and it's drilling out these little holes. Because those little holes are originally there for marking out where I should drill through the whole part to put a screw in. But I ended up changing that. I didn't want the screw showing from the top. I wanted it to be drilled from the bottom. And I figured I'd do that manually because I didn't want to do the hassle of flipping this part over and aligning it. So I suppressed it, and I figured I'd do that manually. So now that we have all of our features, we want to make sure it all works together. So we go up to here and we press simulate on our main setup. And you can see here's our stock. And so let's say, hey, let's cut it. Hit play. So this is showing what the machine is actually physically going to do. This is a one-to-one representation. both in realistically time and exactly its movement. Here, let me speed it up for you and I can show you. Yeah, you can see all the layers. It cuts out the inside. You can see that it's cutting from the inside out. I'm probably gonna, yep, and see I get some errors right there, so I might want to check out on that, see if something's wrong there. You can see how it's cutting the fillet all around the edge. Speed it up just a little bit. Cut around the circle. Ooh, got some errors there. Cutting around the edge. Doing the other fillet there. Cutting around the edge. Now, why is there so many errors here, you may ask? And it's simply because this default tool that I selected, aka all these tools, when I selected a speed and everything, I also decided which tool bit it was using. And in real life, I don't have this spindle and I don't have this bit in particular. My bit's longer than this. So when we go and look at the tool, you can see I selected this 1/4 inch flat end mill bit from the Fusion 360 library, and it's just set up differently. So I know that my bit is longer than the whole height of this part. So I'm not worried about those errors. And of course, you definitely want to check those things every time you get an error, but I know in this case that it's fine. So our simulation, it checked out. The next thing that we want to do is we have to turn this model into something the CNC machine understands. And you may think, oh, we did all this stuff, it should understand it now. Well, the thing is, we have to make a file for that. We can't just save this file. We can't just save the 3D model file and expect it to work, because that won't transfer any of this. What we need to do, we need to right click and we need to hit post process. So I labeled it boat cup holder. I have it outputted to my F drive. What's also really important is I told it what kind of machine is going to be using this. And since the post processor that I have, aka G-code loader, toolpath loader, is called ESDL-CAM, I went for my recents. Otherwise, you can look at all the other post processors that Fusion 360 supports, and you can select which one is your machine. Mine is ESDL-CAM, so that's what I chose. And that's in a .nc file. Sometimes it's a .g-code file, sometimes it's a .nc. Depends on which post processor you're using and what it can read. There's some other cool things that you can do in here, like some extra settings and everything. We don't need to fiddle with that, because I'm going to do some other work in a second, because I have OpenNC file in editor. So if I hit post right now, right here, this is all of the code that just generated. All of this. Look at all this. These are all the locations, spindle speeds that the machine is then going to read and then operate using. You can see here at the very bottom, the machine basically does its last operation. It pulls a G00 and it turns off. Basically, it's a shutdown, which is exactly what you want at the end of the run. And there's some other extra information here up at the top. Basically the name of our file, the name of the tool that we're using to make sure we put in the right machine, to make sure that the units that our machine is running is in millimeters, blah, blah, blah. Tells us our first operation name, which is what's labeled right here. We called that one phase 1. And so it's labeled phase 1 here. Just to make sure that we're doing everything right, M00 basically tells the machine to stop. And so what I do is, we don't want to hit start and have the machine immediately stop. So I'm going to remove the stop command there. It's telling it to stop again after doing a manual tool change, which it's already in our machine when I hit start. So we're going to remove that. And let's look where all the other M00s are. We can see that we used in the pocket. We still have tool 1, so no tool change there. Let's go to our next one. Our drill uses our same tool. I'm still using an M-mill for a drill. Flow 2, that's still our drill, so let's remove M00 there. Same tool, and once again, same tool. So remove all the stops for tool changes. And look at that, there is one last one here. And I see it says no result, saying it found no more M00, so you're probably wondering how does the machine stop? We look at the very end, machine stop is M05. It's not the same thing as M00. So now, what I do is we just hit File, Save. Now, if you want to make sure, if you're doing prototyping, you want to make sure every single operation is going fine, yes, you should leave a copy where there's all those stops in there. That way, so you can do a cut operation, the machine will stop, you can check it. If it's not fine, you can go back in the software here and make those appropriate changes. Like I said, this is version 3 for me, so I came in here twice and made 2 changes. So I made the original model in version 1, made a change for version 2, made a change for version 3. The change for version 2 is me removing these little holes right here, and the change for version 3 was actually, as you'll see in a few minutes, this is actually not just 3 and 21/30 seconds. It's 3 and 21/30 seconds with an additional 1/16 of an inch because the fit was slightly too tight and I wanted to give myself a little bit more clearance. From here, we just hit save. We take our file, okay, our basic cup holder right here that I'm holding, and we go and we put it on our machine. So now that we have generated a toolpath that this machine can actually understand, we now have to put it onto the machine. Now, computer numerical controller, which I was referring to as CNC earlier, actually is a physical controller that this machine has. It's not the computer. It's a separate, smaller computer, let's say. Now for me, it's mounted underneath this machine in the back. I can't exactly show you it because it's dust proof and has like proper ventilation for that. But how do we talk to it still? We still have to use a regular computer to talk to it. So what we do is I'll bring up a software that can read that toolpath, and then it sends all the coordinates and everything to that controller. And then that controller tells all the motors and everything where to go. There's many, many different types of softwares that both can load CAD, CAM, that can run the G-code, aka the toolpath. Not many that can do all, and I'm going to be honest, but there are some. There's different softwares that are capable of doing different steps. For me, for the CAD and CAM, I use Fusion 360. And then for the actual toolpath loading or the G-code loader, I use ESTL CAM. There's many others like Gerbil, which is GRBL. There's plethora of others. All you have to literally Google is like G-code loader or like G-code preview or toolpath sender. I mean, it's all those kind of keywords. Some of them do require certain controllers. Like Gerbil is like you can run on an Arduino, you can run on a TNC, you can run it on like a bunch of small microcontrollers. Very diverse like group of boards it can run on. There's other programs like Mach 3 and Mach 4 that require certain boards that either designed to run specifically that or have been modified to run that. Depends on your machine again. Like for me, I'm running on an Arduino, which is a type of microcontroller. It's very popular, and that limits kind of the area of stuff I can use, but that's also fine because they're very universal. So for ESTL CAM, I'm going to load up my controls and everything, and then I'm going to turn on the machine, and then I'm going to move the machine out of the way. And so basically how that worked was I pressed this button here, which streamed a series of commands to the microcontroller that's underneath the CNC machine that then told motor drivers, that then told the motors where to go. And then since those motors moved, it moved ball screws that physically moved the machine. So there's a whole set of layers of you have to have your model, you have to model it, you have to tell the computer what to do with those commands, and then you have to have a software to then relay those commands to a smaller computer that then tells motor drivers what to do, that then actually moves the motors. There's so many different types of modules for all of these. You can have different computers, different softwares to do all of those. You can have different like microcontrollers. You can have different motor drivers. There's open loop, closed loop. There's hybrid systems of that. There's a whole, it can be very complicated. That just means that there's a lot of ways you can do this. That's not restricting. It may sound restricting, but it's the opposite. So now, let's find a piece of wood for this. And I've already pulled this piece of wood out from the wood pile that's currently overloaded. But here's our piece of wood. Let's grab it. So this piece of wood is generally a lot larger than this piece. But that is okay, because we have to make two of them. So we have to make one piece here, and let's save material, so let's flip this one and put that one there. There. And then we'll have a little bit of extra material that we can use for another project. So I need to figure out how square this corner is. Line up that corner, and we can see that we are pretty darn close near square there. So I know that I can reliably trust this corner to be 90 degrees. And I can save extra material by not putting it right there. We could put this part and cut it out of this piece of wood, but that means that we would waste a lot of material. So the closer we can get it to this corner, the more material that we save over here. Okay, so now that I have this piece of wood generally here, centered-ish on my table, remember we're duplicating this so we can use it as a general template. We have this extra material right here that we're going to end up cutting off. So I don't want to put my clamp too far in, because I don't want to cut my clamp. but also I don't want to put it too far away that it won't be able to be strong enough. And that's kind of generally where it's going to be. But you may think, now that the wood's on here, let's start cutting. We have to wait for 1 second. We have to figure out if this part here is in the same plane as this machine. And we do that by checking if it's square. Now I know that these rails right here move along the same axis as the actual machine gantry moves. So it cuts in the same way, or in the same direction as these rails. At the front of this machine is perpendicular to this axis here, which means this is perpendicular to if the machine moves this way. But it also means that it's parallel to as if the machine moves that way or that way. Hope that makes sense. But that just means that we have to put our part in the same axis. So let's say that our part is, let's just say our part is a little bit of an angle like that. If we want to cut a straight line that way, and we cut it when it's at this weird angle, you can see how much an angle that is. If I cut a line that's straight this way, and we put this back, it's not going to be a straight line, it's going to be at that weird angle. So we need to make sure that this line right here is parallel to right here. And we can do that by taking our square, and since we know that this right here should be perpendicular to this axis here, because this axis is perpendicular to here, we can put this up, we can put this in the channel right here, we can see, oh wow, that's really far off. So I'm just going to tighten this one corner, leave these other 3 corners loose. I'm going to pull that in right there, check it again, a little bit more, and now we're just generally right brushing up against that on that edge. Just give it a tad bit more. Yeah, much better. Has a little bit of resistance. We just want to get that as close as we can so we can use as much material that we can, save as much as we can. So now that this axis here is parallel to this one, we can tighten down this clamp. So, how do we know if the machine knows where that corner is? Because we just put this piece of wood wherever we wanted. We have to tell it by knowing where the end mill is. And what is the end mill? It's the part that we're cutting with. So there it is. That's the part I was showing you earlier. So when we move the machine, it's doing all of that movement and everything, to move the spindle and everything, which moves that end mill. The whole point of all of this is to move that end mill exactly where we want it to. So how does the machine know where it's at? And there's a few different ways to do that. So you can have it as the machine always knows where that end mill tip is with relationship to the machine or with relationship to the part. Obviously you can do both in some circumstances, but in terms of this, let's separate it into those 2 categories. So category 1, if the machine knows exactly where that tip is, you put the part down at one point and it moves that tip based off of the machine coordinates. So basically it knows where the corners are. It says like this point over here, you set a designated point in the machine, you say that is always 0, and you move the end mill in relationship to that point. If it's in relationship to the part, you say, okay, let's say this corner right here of the part is 0. And then you move your end mill in relationship to that corner of your part. You can set it wherever you want in your part, you can set it wherever you want in your machine. It's a difference between, it's either called absolute versus relative. Relative is your part, machine is absolute. Absolute because you know absolutely where it is on your machine. Relative is because you know where it is relative to your machine. Let's just call it machine coordinates, part coordinates. And we need to know which one we're using to be able to tell the computer where to move the machine. Because you can imagine if we said, hey computer, let's set the machine coordinate over here, and then we feed it relative coordinates, it's not going to move the spindle where we want to. It would think that this corner of the part, which the computer thinks 0 is there, and the machine thinks 0 is there, it's going to be cutting our part over here, when we really want our part over here. It's shifting where 0 is. We need to tell it which point is 0. And we can do that really simply by the way we modeled it. We set that coordinate point, our 0, 0, as our bottom left coordinate. So which is our bottom, which is our table height, and left, bottom left, is right here, this corner. So how do we tell our spindle that? It's quite simply, we move our spindle to that spot, and we tell it, hey, that's 0. Just like that. So let's do that real quick. So now that we have the spindle right here, we can see that we have a little bit of gap between their spindle and the piece of wood. So let's move that up just a little bit. And I'm just going to spin this and see if I can feel the material. It's not biting, so I know I need to move it a little bit more. It's biting, so I can pull it back a little bit. Biting again, let me pull it back, and we're just barely grazing it. So now we know that this tool is touching the material ever so slightly. Since this is a 1/4 inch tool, we know that the center line of this tool is an 1/8 inch this way than it is from the part. And then I'm going to tell the machine to move exactly an 1/8 inch that way, and then I'm going to tell that it's 0 that way. So from here, what we're going to do is we're going to go along our y-axis. We're going to see that it says it's -45 millimeters. Well, we know that it's not that. We said that it has to be an 1/8 of an inch, which is not -45 millimeters. So let's change it to -3.175, which is an 1/8 of an inch in millimeters. And let's say negative because it's too far back. So let's now tell the computer to move the y-axis to 0. So absolute positioning of the y-axis 0. So we're making our absolute position the same as our relative. And by hitting enter, the machine moved directly overhead. It's dead center on the edge, which is good, so it knows where it is now. We're going to do it to the other axis. So now when I press enter, it moves directly centered. So now it knows where this corner is, and it knows where that corner is because we know this way and we know that way. And now if I tell the computer to go AY0, it is now, this end mill is directly overhead of that corner. Now we want to give a little bit of leeway. Let's give it 2 millimeters, just in case there is some type of deflect along this edge. So we want to move this end mill this way 2 millimeters and that way 2 millimeters. So how do we do that? Well, that way's positive and that way's positive, and we want to move it 2 units. So we just need to tell it, hey, go absolute positioning of X, 2. Absolute positioning of Y, 2. Oops, excuse me, 2. And so now we're at 2, 2. Which is that way 2 and that way 2. And now we just want to say, hey, actually, that's our new 0. So we just rewrote that into V0. So now we have to find our Z height, and we have to say somewhere on the surface is 0. Now thankfully I've milled this whole top with a cutter, so this is all the same height. So right here, I'm going to say 0. So let's move the machine right there. And from there, we're going to do the same thing, where we're just going to feel for resistance. Yep, just barely touching. So I'm now going to call that, oh, look at that. I've already calibrated there for 0 before, or I've already calibrated on the table to be 0 before. That's a pretty good deviation. So I'm actually just going to leave it like that. So let's bring it up. So now we know our 0 is at the table height in this direction at that corner, and then in this direction at that corner as well. So our center point is that little dot right there. So now we can take that G code and load it up. Very important that even though your X and Y are going to 0, if your part is already in the machine and you are going to send your Z height to somewhere, don't set it to 0 like these. Because if I set it to 0 right now, we're 0. It's underneath our part. We'd be smashing this bit through our clamp, through our part, all the way down. And you know what's going to happen? It's not going to be able to do it. This isn't spinning, it's not cutting, it's going to hit right here, it's going to either break our bit, it's going to stall the machine, it's not going to be happy. So we don't do that. So I'm setting it to 100. So I'm just going to leave it there at a set known number. So now that we have our toolpath loaded onto the computer, I'm just going to confirm that our dimensions are all correct. We have our machine at 0 in the X, 0 in the Y. We have it 100 from the surface of the table. That looks good. Our center is in the bottom left, and that center is also at the bottom of our model. So now that's all left to do is actually turn on the vacuum so we can collect all of our dust and to hit start. stop the cut. I didn't like the way it was going. If we look at it, in this plywood we have this really weird colored, like maybe glue layers, some knots in the wood. I don't really like it. The surface texture on the wood just isn't what I'm looking for. So let me show you what happened. This piece of plywood, it's touching there, it's touching there. You can still see, there you go, you can see the light going through there. When I measure this is about 1 millimeter, 1.5 millimeters, somewhere in between right there. That and combined with, I put in the computer, this is 23 30 seconds. And when I measured it, it's actually closer to 25 30 seconds. So that's a 1/16 of an inch, which is 1.6 millimeters about. So that, with the extra height there, extra height from the piece of wood, is an extra 2.6 millimeters on top of the 2 millimeters that I was already cutting at, which counts up to be 4.6 millimeters. Its depth of cut, I'm holding it at an angle, about 4.6 millimeters. Look at that. I'm pushing all the way down. So that's at the beginning of the cut, but what happened as the cut progressed, and it slid that piece of wood across, it bogged down more and more, until it hit 8.24 millimeters, which is far beyond what this machine can cut at that speed. At least I didn't cut 2 parts and not like it. So, instead of using plywood, I'm just gonna grab a piece of pine, spare piece, I think from a deck or something like that. But I think this will work a lot better, but we have an issue. It's a lot thicker and it's not very consistent. A few ways we can make this work. We can either put it through a planer, which I don't have, so that's not an option for me, or we can put it into the CNC machine with a surfacing bit and we can surface it nice and flat. Here's that surfacing bit right there. It's just got 2 edges on it. It's wide for a router. And so basically what we'll do is, instead of hand programming this in the computer, they do all those steps again. But for here, I'm just gonna put this bit in the router and I'm gonna manually tell it to move in like this zigzag path. That way so we can make it nice and flat. We'll flip it over and we need to tell the machine how thick we want this piece of wood, and we'll tell it from the bottom height up to the top of the cutter. We need to tell it that this bottom of the edge has 0 distance between it and the top surface of this table. And so we need to figure out how thick do we want this. Now I know before we programmed in how thick we want it, but that was because we were trying to line it up with the piece of plywood. Now that we're changing the thickness of our part, doesn't really matter, we can choose whatever we want. And then we'll manually surface it down again to that height. That way so we have an exact piece to that exact thickness. Since we already have this, I figured, why don't we try and see if the cup holder fits nice? And it does for the first part, and then it gets kind of stiff. And I was wondering why. And I looked at this for a lot longer, and I realized there's actually a really slight bow in it. So even though we measured it here, we measured it there, those are the same height, but right here in the middle isn't. And just to confirm it's not the machine out of the whack, right here it says 3 inches plus 21 30 seconds. So we set it to be 3 inches and 21 30 seconds. When I measure this, let me make sure I don't bump it, 3 and 21 30 seconds. So the part that we cut is spot on, which is good. That means that we can dial in a little bit bigger. So yeah, I can't get my calipers around that, so we're just gonna give it, an extra 1/16 of an inch. I think that's all we really need. So I'm gonna add that to the dimensions. It's gonna recalculate all of everything we already did, and we'll be ready to cut again. So we don't really care about this being square to the table or anything right now, because we're just getting it all flat. The table's flat, the cutter is flat, or it moves in a flat plane. All that really matters is that the part is flat. We don't need to make sure it's any pivot or anything, because when you make something flat, you're making sure that it's parallel to another plane. That way so there's no curvature or anything like that. Just completely... Okay, let's see how that turned out. So that's really nice and smooth. All the way across. Looks like we got almost all the way. It's a little bit of overlap here, which means this side right here is a little bit higher than this side. I went a little bit slow at first, so we can see we burned it a little bit, but after we sped up a little bit, that went away. I'm gonna have a little bit of a difficult time getting through these knots, but if I change the depth of cut, it'll probably be fine. But yeah, let's keep going over this whole area, and then when I get to the area where the clamps are, we'll just move the clamps over, and then we'll bring the cutter and cut that area that I couldn't reach with the clamps. And then we'll flip this over and continue. Let's take a look at that. Nice, smooth, all the way across. Since I did it by hand, there are some markings on it. Like this is the burn mark a little bit. That'll sand right out though. That's completely smooth. Overall, I had to remove about, I believe it was 1/8 of an inch difference in height over the whole thing. I ended up removing about 1/16 over 1/8 an inch. Yeah, 3/16 of an inch over the whole thing. Took a while. That's why we usually like to program it in versus do it by hand, but it doesn't really matter. Just took a little bit of extra time. Make sure we can move around the clamps. Ideally, you want to have places where you can screw holes into your piece of wood. I don't really know where the part's going to perfectly sit in it. Oh yeah, look at that. That compared to that. Now when I place it down, that's solid. I just got to do that again. I'm just going to skip. You don't have to watch that. That's okay. I'm going to try and line up this edge as much as I can. Yeah, to avoid, because remember when this cutting path is going to cut down to this channel, it's going to cut in here, it's going to cut all the way around. And I think I'm just going to miss that knot. We're going to be close. Okay, so I've leveled the top of this enough, and I realized I didn't want to keep on doing that because it takes forever. So instead of me doing it, I then took the time to then tell the computer how to do that. It's called facing. So it's going to continue doing this, the rest of it, for me. But it's only going to do it in the areas that we actually need to, which is something the computer knows that I don't really know. I would have to put up the template to figure that out. I did that generally, but it knows way better than I do. So it looks like the part finished, and it finished really nice. I'll give you some close-up shots in a second. So let's move this head out of the way. Yeah, this looks great. Surface finish is pretty smooth. I forgot to program a finishing pass, but it's still really good. I'll give that top layer nice sanding, but you can see all the pine lines that go all the way down, across, back up. This is nice and smooth. This is nice and smooth. I'm glad that we added that versus doing that in post. You can see that it did drill the 2 holes there and there. And that's so when it rains, the water can just pour out those holes. That way so water doesn't get trapped in there. Cut out for the circle. That one came out great. Notice how it's not flopping around in there. Notice how the whole part, it's still clamped down. It's cut all the way out basically. The only thing that are holding it on, I don't even think you can see it. There's a tab 1, 2, 3, 4, 5, and another 5 along this edge. There you go. There you can see them. And that's it. That's all that's holding it in there. It's good and secure. It's nice for getting the last little round bits and everything. But yeah, so now to get it out, we undo all the clamps. We snip those little tabs that we put in there. File those little tabs back so you can't see it. I'll sand the top surface, and I'll ask and see if the customer wants a finishing coat on it. If they don't, it's ready for them. If they do want, well, I'll show you what that looks like. It's time for me to make a second one. That just comes out right like that. And yeah, look how close we were on those edges. That came so thin right there. And that was right against the edge down here. So yeah, used up every little bit of height that we had material there. A little bit of waste there and here, but I'll cut those off and I can use that for other stuff later. Let's get that out. That's oh wow, that's like butter smooth. Now, what we gotta try, see if the cup holder actually fits in there. Oh, that fit perfectly. Snug, no wiggle in it. Only wiggle is maybe a little bit up and down, but otherwise, that's nice and snug. Oh, that looks perfect. I'll give this a good sand down. Otherwise, I think it turned out fantastic. I wanted to give you guys the satisfaction of this. Since these holes were drilled out, but there was a table underneath, and since we set the depth of the drill to be the exact width of this part, you can see how there's this little tab here. Poke right through. Look how smooth that is. You ready for that? Just like that. Paper thin. So now that the part came out almost flawlessly, needs a little bit of hand sanding to it, I'm going to move on to the next piece, because I remember I have to make 2 of these. Before, I had to manually tell the machine where the surface is this entire back half of their part. But now that we've made the change in software that it faces it for us, we don't have to worry about that. So I can actually just clamp down this piece of wood here, and since it's pretty square, pretty flat, I don't really have to worry too much about getting it perfectly flat. And the back half, while it has some marks, it's pretty decently flat. I'll probably sand it to make it a little bit nicer for the customer, but otherwise, it should be fine. We don't have to machine it flat like we did the other one, which had a deviation of around 1/8 of an inch, which is a lot. But hey, wood works. But since we don't have to do that here because it sits nice and flat, we can sit it. So now that we don't have any wood chips under it, it sits nice and flat. So I'm going to figure out where we have our part in it, and now that we have another piece, we can just grab it, put it down right on top where we want it, say, hey, that looks great right there. It avoids these 2 big knots right here, and saves us some room over here if we want to use this end for any other part. So I'm going to square this up just like before, tell the machine where to start at just like before, and hit run just like before. And I gave it a quick brush down since we didn't have a finishing pass programmed because I was going to sand it anyway. It's ready to come out, so let's move the head out of the way, get these clamps undone, and see what part we have. Let's cut those tabs out. See, the holes went through this time. Yeah, but you can see how the back looks a lot more rough compared to the side that we faced completely down flat. It's a lot smoother on this side, but that side's not even that bad, and you're never going to see it because it's going to be faced down. All the good stuff right on top. You can see where the areas that I didn't do a finishing pass on is when I hold it at an angle. And that's just because our cut width was the same width as the bit, which left just a hair bit of material left over. If we're making 100 of these, I'd make an extra pass. So now we got 2 pieces, sand and stain. Let's see if the cup holder fits in this one too. Should. Exact same model, exact same parameters. Yeah. There's a little bit of wiggle. No, that's just the cup being weird shaped. Like we said before, it's kind of oval. This way, nothing that way. Same thing here, nice and snug. It's perfect. Yeah, so after sand and stain, we'll glue these in. I grabbed a piece of sandpaper, and since in software, we didn't tell the machine to run a finishing pass over all of this, we just had a roughing pass, which meant that the bit moved over the same diameter that the bit is, which means in between where we have the bit on the pass 1 and the bit on pass 2, there's a little bit of gap right in the middle, and it shouldn't be there, but just due to when it cuts, there's a little bit of wiggle and everything. There just leaves a fine, fine little bit of fibers from the wood left. And then since we didn't tell the machine to do a finishing pass, which would be like a very large overlap, let's say like a 50% overlap, to knock off those little bits of fiber, we have to do it by hand instead with a little bit of sandpaper. And that's not going to take long. That's just going to be just a clean wipe down, and then it's ready for some stain or some oil. Just getting any little areas that I missed before. There we go. Looks great. This one looks even better. And you want to know how I know that I'm not a woodworker? I'm going to throw away my used sandpaper. Okay, so let's wipe these down so that none of the dust is still laying on here. Blow it off with some air compressed. No, I'm so tempted to use the air compressor, but the amount of times where I'm told that air compressors spew out just a little bit of oil or a little bit of water, and that can mess up finishes. But at the same time, like, I feel like that's going to do work. I have some Danish oil that works really good for this kind of stuff. I didn't use an air compressor. I felt like enough woodworkers would have been mad at me enough. So squeezy bottle it is. Now I don't want to put this oil on over the CNC tape. Oh, I don't even want to set that down. Because if any of this oil gets on the CNC table, anything I set down on it has the possibility of staining. So I want to keep that as far away as I can from it. That being said, I'm going to do it right here. No, I don't know. Should I joke about that? I feel like it's a bad joke. Anyway, not at the table. Okay, let's get this cleared up. Nice. Let's get you a top down. So let's get the oil and let's get a towel. Well, I'm really supposed to use a regular rag. I don't want to waste a real rag, so I'm just going to use some Blue Shop towels. Hopefully it doesn't absorb it too much. And this mat, hopefully I should be able to clean up the stain or the oil off of it. But just in case, let's get something so I can set these down and not get any oil pooling on the mat. These are just some wood cut-offs from past projects. They're about the same height. It keeps it off the table. That's all I need. Just like that. Okay, so let's get this thing open. So I give up and use tools. Jeez, I hate these child safety locks. There we go. Okay. I'll start wiping it down. Just gonna do a thin coat first. You know what? I should probably put some gloves on. That'd be a smart idea before I get really any oil on my hands. This is the bottom, so I'm not really worried about it looking the greatest, but you know, if someone looks underneath, I want it to look like it's at least stained. See if we can get a comparison photo. Might be a good thumbnail. So let's move on to this one now. I'll give you a close-up. Just looks like it transforms into a different wood all of a sudden. Now, one thing I did miss is that these drainage holes, I'm just standing a little bit off axis and I can see that they're a totally different color. And just so that, you know, someone doesn't see that and get, you know, a little upset, I'm just gonna grab a Q-tip. I'm gonna go all the way through there, wipe that all the way around. That looks great. Now, since that got all fuzzied up, use the other side. I'm gonna give those a minute to dry. And then I'll see if they need a second coat. They probably do, because the oil's going to soak into the wood, and then the surface might be a little bit dry. And I'm purposely leaving these holes without stain. I know I did wipe once in there, and I realized that I have to put a little bit of glue in there, so the cup holders stay in there nice and firm, while they do fit very snug. A little bit of glue on something like this that you don't want to get blown away goes a long way. So let's give that a minute. Okay, so I grabbed this halfway through the time lapse, and I just want to make sure it was 15 minutes, and it is. So I'm going to give this another light coat, just in case if it needs it. There we go. Use the fresh side. Now the reason why I'm getting a lot more absorption on the side than I am the top is because the grain is on the side. And so the little water vessels that are usually in the wood just absorb it all up. You can see how this is much darker than the top. And that's just normal. And you can also notice that the bottom here is much lighter than the side over here. That's because the wood grain goes this way. And that's just normal. It's just how wood is. You can see this one's a little bit darker than this one. Yep, but now, since that one's been drying for a bit, you can see how much darker this one is now. So let's do another quick time lapse of that. Hi, well, it's been about half an hour. Hopefully we saw a color change of it absorbing in and whatever. But anyway, I'm going to leave this overnight, and we'll pick up tomorrow. It's been over 24 hours. This is how it ended up looking like. Not that much different, but that's pretty good. All the oil absorbed in. So listen, now let's go and take them and go put it on the boat. There's some broken here and there.
Yeah, 2 inches on each side.
I love aluminum.
Yeah, I was actually talking to Larry.
There we go. It's on. So in the end, CAD versus CAM versus your toolpath loader, whatever you want to call it. CAD is for designing your model. CAM is for taking the model that you did design already and turning it into toolpaths and everything that your machine will understand. And then the third part, the thing that actually runs your toolpath, whether your toolpath loader, your post-processor, your G-code loader, whatever you want to call it. All it does is it takes the code that was generated in your CAM software and it tells the motors to move. It tells them where to move, it tells them when to move, how fast, how slow, the spindle should be this direction, that direction, how fast should it go, controls all of that. So designing model, designing how the machine moves, making the machine move. That's the difference. Now you know.